Hi everyone, welcome to 151st Stanford MedAI Group Exchange session. This week we have Trong from University of Arkansas to talk about their work on a dataset and baselines for 3D volumetric Scanpath modeling. Trong is a PhD candidate at the University of Arkansas Fayetteville, working under the supervision of Dr. Nang D. His research focuses on the intersection of expert behavior analysis and deep learning, specifically applying human eye gaze analysis to transform and enhance deep learning models. Um, Prior to his PhD, he was an R&D researcher in Singapore where he developed digital twins technology, including talking face generation and 3D human models for metaverse applications. Trong, thank you very much for joining us today. Before we start, do you have any preference on how you would like to take questions? Can we interrupt you in the middle, or do you have like designated breaks in your talk?
Yes, feel free to interrupt me. This is a very long slide, so just feel free to interrupt me.
And thank you, Trong. So in that case, everyone, let's try to make this as interactive as possible. And without further ado, let me hand it over to our presenter.
Okay, thank you for the introduction. So, hello everyone, my name is Trong Thang Pham, and advisor by Dr. Ngang Lê. Today I will present my work on eye tracking research in medical. The title is CT-ScanGaze, a dataset. It is a dataset, and I also propose a baseline for 3D volumetric Scanpath modeling. This is a collaborative work between many institutions. Um, and I'm happy that we managed to push it out to ICGV next this year. So, okay, let's get into it. I will go through there's some main outline here. Well, I will go through motivation contribution where I will try to wrap up our main contributions so that you have a general idea of what we do. And then I will go deeply into the technical details of data, method, and experiments. So, like previously I said, feel free to interrupt me along the way and for the motivations. Okay, so right now, computer-aided diagnosis tools are difficult to trust because they only learn from the final labels and diagnosis notes. They miss one important thing, I believe, that the unspoken part of how radiologists work. Uh, it is a tiny ways a person looks at a scan that carry meaningful information, but they won't be written down. So one natural question came to us that is a radiologist skill just the diagnosis and the annotations, final reports, or is there extra information hidden in how they look at the images? So for example, a source, pauses, or the path of their gaze across a city and the timing. We believe the answer is yes. Radiologists send a lot of information through their behavior, and every eye movement and attention shift can reveal parts of their thinking. So if we can manage to train the neural networks to decode those patterns, AI can learn from behavior as well as the final labels. That will create a system that can understand the same silent signals that humans use. So AI human teamwork will become more interpretable and natural. So thinking of it this way, so one of the application that we really want to implement right now is when a trainee novice radiologist uses our system, they can get feedback on not only what they diagnosed wrong, but also where they should look for it and the order of what to check. So just like how a real teacher hold our hands and teach us. And this is a general figure of the directions in check X-ray. So we have many tasks available that we can do. They have eye tracking data, report data, full a lot where we can do scatter prediction, classification, explainable report generation as well. However, when we try to do that on CT, it's not easy because we don't have the data for gaze or attentions. We only have the report data or the findings data. So we have some sort of explainable report generation and explainable classification based on self-supervised learning, but that basically it. We don't cannot do the scan path prediction even if we want to. So what we do is to try to tackle it by the first step, that is to collect the data, and then we'll introduce first CT scan vibration baseline on this data. So just two small steps for this direction on CT. So this is overview of illustration of our data collection and processing time pipeline. Uh, the data collection, this right here, on the left side. It shows a setup where radiologist examines a CT scan on the screen, uh, equipped with a TOBI tracker and a microphone to record the audio. And we will have the video, the icon files, report audio, and eye tracking data. They are the raw data. And then we have to process somewhat so that we will have a 3D scan path, 3D eye tracking data mapped with synchronized with the report and the finding. So, in practice, this is the room where we record data. We has to make it has some good lighting. This is me, and the radiologist will sit in this same position as me, and they must sit straight, keep their head stable, but comfortable enough so that they can actually focus on reading the image. And this is the Tobii eye tracker in a red box. This is the microphone, and this is the laptop, the device that record data, and we save every recording we have. Uh, can you hear the audio? Yeah. So this is one. Okay.
I think, Ron, we can hear you, but if your video has some
Uh,
audio, no.
that's too bad. But the Regis is actually talking in when they are trying to scroll through the slide of the CT.
Sorry, I missed. What are
I'm
the
not sure
red
it makes.
circles? Is that where he's looking?
Oh yeah, the red circle is where he is looking.
Okay. Okay. The
I'm
So,
not
radiologist.
sure where to
Okay.
open the video audio here.
Strong, one quick question. So, what devices are you using? Are you using headset or you are using any other
Uh,
device?
it, yeah, it's a Tobii Eye. It's a
Okay.
device
Okay. Got it. Got it. Yeah.
right
Yeah. Yeah.
below
Yeah.
yeah, yeah,
Okay.
yeah. So this reader here is an OHIP viewer for it can open X-ray or CT the same, and you can use some tools. Our current data doesn't take into account the tools. It's only had the CT and the gaze position on the screen and the report. Okay. So this is a static example from our datasets. We have three CTs are viewed and concluded with radiologist report on the right columns, and for the left column they are the gaze pattern when the radiologist go through the depth of the CTs. So we have multiple slide. The index is the slide number. So for example, the first we have the slide number 0 to the uh, 580, 89, and you can see that the pattern they will go over to a, a certain slide in the middle, and then we go back, and then you go more deeper inside and just go back, and at a certain point they will go through all the slides. The depth is the slide, and I just described wrong. The index is the index of the fixation, and the depth is actually the slide. So let me say it again. So the depth, think of this like a slide of the CT, and they will all go to the middle of the CT, and they go back to the beginning, and they go do that multiple times, and at certain point they go through all the slide and then will go up again. So we can some sort of infer that they think around this area, this area is there's something abnormal about that area. We can think that way. And if we lay out our slices, we can see that the physician move quickly to the end. Uh, they have a habit of go through quickly to the end, and they will go back to the area that they think that there are some abnormality. They're going back in the middle. In this example, it looks like they only focus on the middle part where the top and the bottom doesn't have much abnormalities. Okay. So after recording our data, we have around 900 CT-GAZE pairs. Where we split into training, validation, and test set, we have around 600 pairs for training, 90 pairs for validation, and around a little bit lower than 200 pairs. And the chart below is the findings label. So we have multiple findings, but most of them will lean toward the pneumothorax and opacities and pleural effusions. Also, they are the common findings. And for the number slide, our CTs, when we take some number, we have around more than 100,000 slices in total, but the average is around to 186 slices per CT in average. And this is when we try to train the model, we have to do another step. We cannot just use the original fixations because they have a lot gaze recorded. They can reach to 2,000 fixations per CT, and we have to employ a simplification algorithm from the multi-match for the multi-match toolbox online. Is a tool that we usually in the community of tracking research community, they usually use this toolbox to simplify the eye gaze data. And this process will reduce the poise to a acceptable amount, but it's not too much, but the shape has to be as close as to the original scan path as possible. And this is on the Z, which is the depth direction. And this is on the X direction. And this is on the Y direction, which is the height. The X is the width. But there's another thing I want to point out that our radiologists, I think they mostly focus on the middle of the image. That's why you can see that the variance of the scan path between the of the X and the Y scan path are not fluctuating and not a lot, always around the middle of the image. And let's go through our method. So this is our method. This is a CT searcher. We name it. It will process a CT scan to predict a 3D scan path. It looks complex, so I will try to decompose the step into just a few main steps. So the first is that a 3D visual encoder will take the original CT. They feature, we also have a special top token tall right here above the F feature, and then we go through MLP and flatten it out so that our transformer encoder can use it. We also have to do a small modification with 3D positional encoding. This is what we suppose, and then we add it to the tokens, and then finally we fit it, put it into the encoder. After that, we do the coding step where we actually have to apply the 3D positional encoding again so that it doesn't lose the positional encoding information from the transformer encoder. And we also have some set of learnable query queue. Each of these learnable query will have to tell us later when we decode the attention heat map that if we the attention location distribution of 3D heat map and if we stop or we continue predicting. After the transformer decoder, we have the R, the feature R. It will go through a duration predictor head where we receive the T, which is our duration, and then it will through another fully connected layer. This is matrix multiplication with the feature from transformer encoder, and finally go through a softmax so that we have the 3D volume. This Y hat here is a 3D volume. It has to be the same shape as the original input volume, CT volume. It will be from the value range will be 0 to 1. It tells us the distribution of the possible fixation at that step, including the stop token. So this stop token will tell us that if the model wants to stop there, and we will discard any operation after that stop token. However, there's a problem. Our model is a transformer model, and we all know the transformer is very hungry for data. So we at this step, we have to think of a way to get more data. And one way to do it is to use existing data from 2D, which is check X-ray. So we collect the data from the eye gaze data and the reflect data. So in total, we have around 3,000 pairs of check X-ray and fixation. And for check X-ray, we can simply transform it from 2D to 3D by using check X-ray to CT method. Thankfully, we have some work on the community has some work on that, so we can use those two. And for the Scanpath, we have to use an assumption that is, well, the Scanpath is going from, we have to go through from the top to the bottom of this check X-ray so that it will have the axial viewpoint. So there's some, we have to assume that it will be in the middle of the cities. So this will be one of the assumptions we have when training the model. That's why when you see the example here, they are just in the middle of the city. And then we have to use another assumption to make the data bigger, because right now we only have 3,000 data. Each physician has the assumption that they belong to a Gaussian distribution. We set a standard deviation, and then we sampling from position of each vision. So each vision we have X and Y. Let's assume that it is the mean, the middle point of the Gaussian distribution, and we have the standard deviation. And with those two information, we will sampling a new point, and we do that multiple times. We will get a lot of data, which will follow our assumption of what Scanpath is and what cities will look like. And then we train our model on this data so that the encoder can somehow adapt to the CT features. and the decoder can somehow get used to predict the fixation-like sequences. So it's a little bit technical here, it's very tricky. After we have everything ready, we will do the experiments. For this evaluation matrix, we use on two aspects. The first is the Scanpath based matrix. They are the standard Scanpath regression matrix from general domain. We have scan match, the multi-match, and the string edit distance. They measure different aspects of our scan path. For example, the vector, the direction, or the duration. And we also have to measure the saliency aspect of it too. So we have the correlation between two distribution, the KL diversion, and SS is a heat map, but it is normalized. It is a normalized saliency matrix. And we found that with both trick in our model, we achieve a state of the art. The first trick is the symbol transformer network, and the second trick is the pretraining method. So other methods doesn't have the same pretraining data that is, they already train on our small subset. And in order to really compare on our data, we have to modify almost half of the network. So like we have to change their encoder, and then we also have to add the 3D positional encoding, and then we have to change the final output to match with 3D scan path. So technically, this is a lot of work with. If you want any of this method on this table, you can get one, and it is a new baseline by itself. For the qualitative comparison of our method and other state-of-the-art, we have hat and gaze from our SP doesn't perform quite well. I think because, for example, for the hats, they have they predict in a very different way. Like, let me show you. They have the full fixation heat map, and it's quite similar, but they do is just depend on the previous point, and then predict like it's sequentially, it's autoregressive, it's sequentially, and somehow that doesn't work quite well. But if we do it in our way, where we try to fit a bunch of queries into the model, it works better. For the eye gaze ISP, they are quite similar to us, but they are more the network is quite complex, and it turns out they doesn't learn well on our data. And our method can manage to somehow match with the final ground truth, where it show some sort of fluctuation, random. If we focus on only uh, local part, and when we zoom out and see, it quite follow the pattern of the ground truth. And we also have to compare with because our data is collected from two sources of radiologists. So we can have two different route truth. So to assess the potential learning bias toward one's radiologist style, because our model is trained on two radiologists, and it doesn't have the input of which individual to focus on. So it has to predicts the general scan path. That's why we need this step. And we can see that the performance is generally the same, with a little bit leaning over to radiologist 1, I think. But generally, they are very similar. And for the ablation studies, You may ask what visual encoder to use. Actually, we only use what available at that time, which is the swing unit encoder and CT-VAT. CT-VAT is an encoder that used in report generation on CT, and swing unit is just a segmentation backbone. And we saw that swing unit is the uh, better method in this case. For the table, on the left table, they are the ablation over the 3D positional encoding and whether we use pretraining, what is the effect of it. So training without 3D positional encoding ultimately will make the model fails to learn, and training with pretraining, the first column, which will slightly help the models. And finally, conclusion. So in conclusion, we propose introduce a CT-ScanGaze, the first public CT-ScanGaze dataset, and the first CT-ScanPath prediction baseline. So these two simple things take so much time to reach this point, and I'm really glad we made it. And for the discussion, this open what can be done from chemistry domain that CT previously cannot. For example, asking the gaze associated with the disease, or try to understand the tension behind its fixation. So those two works are what our lab published in WCV and ACMMM this year. So for visual search, the first things that I mentioned is the visual search where we from a check X-ray and the query of what finding to look at, the model will generate for us the scan path that is similar to what radiologists usually look when they also know what finding they need to focus on. And for the intention interpretation, we have the check X-ray and the scan path, any scan path, and what the model job is to infer what that scan path is actually trying to look for. So, for example, at the end fixation example, the model has to predict that the radiologist or the user is trying to look for lung lesion. It will be the middle step before we do something else behind it, like understand the user, its label, downstream task, any task. And that's it from my talk. Thank you for everyone for listening. This work is based upon work supported by NSF and NIH, and I also have published the data and code of this work.
Thank you very much, Ron. Thank you for this excellent presentation. So before I open the floor for questions, let's just give our speaker a virtual round of applause.
Thank you.
And if our audience have any questions, I think you can just go ahead and ask, please.
I can start with one.
Sure.
So, very interesting talk, Tom. Thank you. So, did you also think about viewing the slices as just 2D images and then trying to see if the gaze data can be used for improving that, or were you always considering it as a 3D problem?
Well, actually, for the 2D, when we do the training the model, we actually have this step where we try to transform the check X-ray to the CT. So thankfully, this helps. We have to, just to mention again, we have two steps when we try to use the 2D scan bar data. First, we transform the check X-ray to CT volume, so 2D from 3D image. And then from scan path, we have the X and Y on the screen. We have to transfer it to X, Y, and Z, which Z is the depth. So we have an assumption that Z will be in the middle, which is 0.5 in the middle of the CT. And that is how we create the 3D synthetic CT data, scan path data. And it's help a little bit, slightly. I'm not sure if there's another efficient way, maybe because the CT to check X-ray methodology is not perfect right now. There's still a lot to improve.
Thanks.
But definitely, I think we can somehow map between because, well, they are assume that they are from the same patient. It would really have to only take a CT, check X-ray and can somehow, without taking the CT, and can infer it correctly.
Thank you.
There is one question. Ramon, do you want to go ahead and ask yourself? Or
Yeah. So yeah, great presentation, really interesting. And I was wondering when it came to the scan path, let's say that the model produces, if I'm understanding correctly,
Yes.
could that differ in length compared to what the doctor is seeing? And would it be worthwhile to investigate, if there's significant differences in the scan paths?
Yeah, this is a great question because, well, the model has to be limited to a particular number of queries. So as a result, they can only predict that much fixation. So, for example, currently I have 400 queries, so I can only predict 400 fixations. And from the doctor, usually they look longer. The longer they look, the longer sequence will be. So ideally, we would want to somehow let the model predict as much as possible, the same as the doctor. But right now, we can only limit it to a limited number of physicians sequence.
Yeah, that's fair. It'll be interesting to see if it's possible to extend the sequence as well.
Yeah.
do we have any more questions? If not, then I think we can give our speaker another round of applause. And thank you very much, Trong. If anybody has any questions later, we can put them in touch with the author. Thank you. Thank you for the excellent presentation, everyone. See you guys next week.
Thank you.